In this video, we're going to show additional examples on how to use frequency domain analysis. This example is an exercise on phasor manipulation and is simply direct substitution. So here are the solutions. So I won't go over with the solutions except in this second requirement, which you might encounter a math error in doing this operation. So the workaround here is to first ignore the negative sign and calculate this, and after that you can multiply the result by -1, and that should give you the same answer. This example pertains to a series RC problem, and this is the same problem that we did on one of our examples in time domain analysis. So this is a repeat, except that we're going to use phasor analysis to solve the problem. One note is that when we are required to get the quantities in lower cases, we usually refer to the time domain solution of those quantities. So for the current here, the final answer should be expressed in time domain form. Likewise for V sub R and V sub C. Okay, so the first step is to convert the circuit into a phasor equivalent. So this is the source, this is the resistance, it's still the same, and this is the capacitor. So this is the transformation to phasor equivalent. Notice that we've replaced the lowercase quantities with uppercases, so V sub R, V sub C, as well as the steady state response I. So next we compute for the impedance in a rectangular form. So you could also compute this in polar form if you wish. And the reciprocal of that would give you the admittance. So now that we have the impedance, we can now compute for the current in phasor form, and also for V sub R and V sub C. So notice the usage of the uppercase letters because or since we're dealing with phasor quantities. And now that we have the phasor results of I, V sub R, and V sub C, we can now determine the time domain expressions. So this is for the current, this is for the voltage across the resistance, and this one is for the voltage across the capacitor. We can check our solution. If we add the phasor values of V sub R and V sub C, that should give us the phasor value for E. So this is really just a KVL equation used for checking our values. Okay, let's go to the third example. So this is again a series RC circuit, but this time the elements are given in phasor values already. So we are asked to determine the impedance, the phasor I, and the time domain I. So for Z and I, we could compute the impedance by simply writing R plus JX of C and leave it as that in rectangular form. And then we could compute for the phasor I. That should give us this result. And now, how do we compute for the time domain I? Now, since we don't know the whether the source came from a time domain source expressed as a sine or a cosine function, we could have two answers here. So we could either express our time domain I as a sine function and or as a cosine function. And we can use a variable omega since it is not specified what is the angular velocity or the frequency of the source. So let us proceed to a slightly more challenging problem. So here we have a series parallel combination, and the first requirement is what is the total impedance of the circuit. So this question means that we are required to compute for the equivalent impedance looking at these terminals of the source. And then the admittance of the circuit, which is simply the reciprocal of the equivalent impedance, and the voltage across the capacitor. Again, it is expressed as lowercase, meaning the required answer here should be expressed in time domain. And then the RMS voltage across um, the inductor. So let's say this is V sub L. So here's the solution. So again, we first express um, our circuit in terms of its phasor equivalent. Take note that we have omega equal to 1 radians per second. So this is the phasor equivalent of the circuit. So we proceed by computing for the equivalent impedance or the Z sub T here. So this part here is in parallel with this one. So we get the equivalent impedance. So this is this part here. Then the combination is in series with the 1 ohm. So we add 1 ohm and we got here this result. So we take the reciprocal of that and we get this result. So we could then compute for our phasor I, and that is simply the source divided by the equivalent impedance, which is 2 minus j. Now take note that we have written the source simply as 10 volts. We could have written it as 10 angle 0, but the 0 here has actually have no effect on the solution, so we could ignore it actually and simply write 10. Now, how do we get the voltage across the capacitor? So one way to look at it is to first compute for the current that flows through the capacitor in this direction. So to get this current, we could use current divider because we have a current that flows towards a parallel combination. So this branch and this branch. So so first we're going to compute for this current, and then upon computing it or after computing it, we can then multiply it by the inductive or capacitive reactance of the capacitor. So this current here is this portion. So we said that this current is equals to the current that flows through the parallel combination, which is we know to be 4 plus J2, and then multiplied by the impedance on the other branch, divided by the total impedance of this branch and this branch, which is 1 plus J1 minus J1, which is simply A1. And we multiply this entire thing with the capacitive reactance of the capacitor, and that should give us this result. So from this, we could now extract our time domain solution, which is simply this one. So we use the cosine because the source that we use has a cosine function. So we made that function, that cosine function of the source, as our reference. So when we turn back to time domain form of the solution, we should use that reference function. Now, how do we compute for the voltage VL? So that would be the same procedure on how we computed for the voltage across the capacitor. That is, we first get the current here in this direction. So that would be this current. So it is this current times this impedance divided by the total impedance of the two branches, which is again is a 1. And then we multiply the whole thing by the inductive reactance of this inductor so that we could get a phasor voltage across it. So this is our answer. Now to get the RMS voltage of V sub L, we know that this will be the amplitude of the time domain expression for V sub L. So we just divide that by square root of 2, and that should give us its RMS voltage. In this example, so we're asked to determine the current coming out of the source, so I sub naught, and this current I sub 1. Now to get current I naught, what could we do is simply get the equivalent impedance of this. Then let's say this is the Z sub EQ. So I naught there would be simply equals to 60 angle negative 30 divided by Z equivalent. Okay, and we could also proceed to compute for I sub 1 once we compute for I sub naught. Now there's a bit of a challenge here because um, this part here, is really a delta um, part of the circuit, or this one is a Y. So we could not directly simplify this without transforming that part of the circuit. So for this example, I won't uh, be discussing the whole process of the solution, but I will simply give a guidance on how to proceed with solving this problem. So what one way to one approach for this is to um, assume this element, this and this, as a delta network and replace that by a Y network composed of Z sub 1, Z sub 2, and Z sub 3. So once we get those impedances, we could replace that delta network, and that would result into uh, a network that looks like that, which can now be simplified because C sub 3 is now in series with 10 ohms, and the combination is in parallel with this part here, and this whole combination is in series with C sub 1 and the 2 ohms, and therefore we could solve I sub naught. Or we could treat this part of this circuit as a Y combination. So therefore we could replace that by a delta represented by C sub 1, C sub 2, and C sub 3. And once we got those values, we can replace the Y network, and that should be the resulting network. So now this is now parallel, which is in series with this, and the combination is in parallel with that. So we could again easily solve for I sub naught. Okay, so um, as an exercise, you may want to solve for or to complete the solution so that you can have a feel of how to solve or transform y delta or delta to y uh, transformations. In this last example, we're required to get the impedance between the open terminals. Um, we could have hoped to simply add the values of the elements after converting them to phasor, but the presence of the dependent voltage source makes that impossible. So our first step here is to assume that we connect this circuit to a sinusoidal source. And after doing this, we can convert it to its phasor equivalent, which looks like this. So this is the source, and so we convert the small lowercase quantities into uppercase quantities, and we also replace the inductors or the circuit elements by its phasor equivalent, and we have here Z sub in. Now take note that since we already have a source, that means that we should have a current, and that current should also be expressed as its in its phasor form. Okay, so these are the computations for the inductor and the capacitor with regards to its phasor equivalent. So since this is now a closed circuit, we could write a KVL for that. So this is the KVL equation. Now the voltage V here, which is the voltage across the 50 ohms, can actually be replaced by 50I by Ohm's law. Then after simplifying the circuit, we will have this, and transferring I here, that gives us this, which is really the impedance between the open terminals, because this ratio is actually the impedance. which gives us an answer equals to this one. So Z in is equals to this one. So that's it for this video. And on our next series of videos, we will go over with the methods of analyzing AC circuits in the same way that we did this in DC circuits. We learn how to use mesh and nodal analysis. And on our next video, we'll also um, see how we apply these techniques in the context of AC circuits.